All right, testing the audio. All right. Okay, so the problem over here is the strain rosette shown is used to measure the strains of a structure made of AISI 302 stainless steel. A gauge reads 45 times 10 to the negative 6 inches per inch. Gauge B reads 200. Gauge C reads negative 250. Find the sigma 1, sigma 2, and the tau max. Report your answers in KSI for the stress transformation step. Please explain using Morse circle, not the stress transformation equations. So for this example, we're going to be using Morse circle. And I have over here on this piece of paper the steps that we follow. For this problem, we're first going to give our strain gauge data, which was given. Then following that, then we're going to use the strain rosette equations to get a state of strain. Following this, we can either go either branch on this flow chart. For this problem, we're going to be going on the left side. So generalized Hooke's law that then gives us a state of stress. And then after that, we'll be using the Morse circle and principal stress. So as the problem goes on, I'm going to bring the paper back and continue on showing the next steps. So the first step is we have our strain gauge data. We're going to write that down. So we have epsilon A, which is this one right here, and that's 475 micro inch or inch. And then for B, we have 200 inch per inch. And then for C, we have negative 250 inch per inch. Now for this equation, what we can do is, since this is on the x-axis, we can then set for our strain rosette equations, we can set the strain of A equal to the strain of X, which we're going to do right here. So in that equation, we eliminate one of the rosette equations, which allows us to have it simplified into two equations. So writing down those two equations, or in terms of B, it's going to be x cosine squared to the B plus, and then y sine to the B plus, then our gamma xy sine B cosine B. All right, and then for our C value, for this we already have our A equation, so we don't need to use that. For our C, we then write that down. X cosine squared theta C plus 2y sine theta C, and then gamma xy sine theta of C and cosine theta of C. So now we're going to start filling this out. So if we look here for our x, we already have it. It's our 475 since we defined our A as our x, since they're aligned. This is a reference point. Obviously, cosines and sines are those. Our two unknowns in this situation are the y and then the gamma. In addition, for our theta b in this case would be negative 60 degrees, or you can do all the way around 300. For this problem, I'm going to be doing negative 60. And then for C, if you base off this axis, we can do negative 120. So we're going to write those down, those equations. Negative 60 degrees plus y. This is our unknown. Oops, forgot the squared over here. Squared, and then we do a negative 60 degrees. Keep moving on. Gamma xy sine of 60 degrees, cosine of 60 degrees, and my hand is kind of bumping into the little tower I have set up. All right, so oops, we already know what our E of B is, which is 200. So what we're going to do, this is just a regular value. We're going to move it over on this side and then solve for these two. So I'm just going to quickly do that on the calculator. All right, so on this side we have 81.25, set that equal, and then for this one, sine squared of -60, that's gonna be 0.75, so let's have our variable, then 0.75, and then plug in this one, sine of 60 times cosine of -60. Don't want to mess that one up. And once we solve it out, plug it into the calculator. And for that value, we have -0.433. All right, and then we're going to do the same thing now for the C. So starting off, what is the value? -250 is then equal to 75 cosine squared of -120 in this case instead of 160, since we're referencing from this point. So two -60s make a -120 in this case. And we'll just finish solving it out or writing it, plugging it in. Sine squared -120 degrees plus, and then our gamma, xy, sine of -120 degrees, cosine of -120 degrees. All right, and now we're going to solve this out. This and then subtract that to move it on to the opposite side. -250 minus, and then we're going to do 475 cosine squared, and then of a -120 degrees. So then we get on this left side, we have -368.75. And then we solve out for here, sine squared, and then we do -120 degrees, solving that out, and we have 0.75. So we have e of y, which is then equal to 0.75, same as before, and then plus we have our gamma. Solve the next thing for sine of 120, -120 degrees, and then cosine of 120 degrees. Solving that out, and we get 0.433, same as before, but the negative switch. So in this case, we have equation 1, equation 2. We have two equations, two unknowns. This can be solved in multiple ways, but in my case, I'm just going to do a matrix multiplication on my calculator. So let's set up this matrix, 0.75, and then -0.433 in this case, then over here, 0.75, and then a positive 0.33. That is our A matrix. Then we have our unknown matrix, the strain and the Y, and our gamma value. And of course, this will then equal our B matrix, which is the values that we have over here. So 81.25 and then -368.75. All right, and then this is just a matrix that we can calculate pretty simply. A inverse to -1 multiplied by the B, of course, gives us our unknown values. So I'm just going to have this written down ready, and I'm going to spend some time making the matrix right now. Matrix, and then we have 0.75, next value is -0.433, next row 0.75, and then 0.433. All right, then making our next matrix for our B matrix, in this case, the 81.25, another one, 1.25, and then -3.6875. And then have the two matrix sets, matrix A inverse to the -1 times the B matrix. And from that, we get our final values for this as -191.667. And then for our other one, we have -519.630. And obviously in this case, this is in terms of micros or pico, since everything else follows. So now that we finished that, if we look back to our flow chart, we got our strain gauge, we got our strain rosette equations, we use those, and now that is our state of strain. So now we are going to go on the left side. We're going to use generalized Hooke's law to find the state of stress. So I'm going to be switching over to another piece of paper. All right, so before we solve for this, we need to have 3 constants. And these are the constants for the AIS steel. So we're just going to write that out real quick. AISI steel. For this, we're going to need the E, modulus of rigidity, elasticity, and then Poisson's ratio. Have a G, and then Poisson's ratio. So for these 2 values up here, we can just look into the textbook and then convert it over to KSI instead of PSI, which is originally in, since the final problem asked for the answer in KSI. So if we look at the book for this specific steel, ASI 302 stainless steel, for our E, we're going to have 2800 KSI. Our G, we're going to have 10800 KSI. And then for Poisson's ratio, we actually have to solve that out. And for the equation for that, Poisson's ratio is equal to negative strain lateral over the strain longitudinal. In other words, y, strain y over the strain y over the strain x. So we're just going to write that out, minus, and then of course we had minus from before. This right here, the y, 191.667 all over 475, which was our x from the very beginning, and that gives an answer of, let's see, plug that in the calculator, negative makes a positive, 191.667 divided by 475, and we get a final answer, negative 40, not negative, 0.4035. The 2 negatives cross out and make a positive. So that's Poisson's ratio right here, and we're going to put it right here, 0.4035. So now we have these values. I'm also going to write down our sigma x and sigma y and our tau just for it's easier. We don't have to keep flipping between pages. So we know our sigma x is equal to 475 from the very beginning. Sigma y, we just solved it. It's the 191.667. And then for our gamma xy equal negative 519.630. All right, so now that we have those values, we're going to use something called generalized Hooke's law. And this is what then gives us a state of stress, which we can then use more circle. So moving on, generalized Hooke's law, let's write that down. Sigma x is equal to E over 1 minus Poisson's ratio squared. And then we're going to have the strain in x plus, and then Poisson's ratio times strain in y. All right, so if we just, all we have to do, we have all the values, we have E, we have Poisson's ratio, we have all the values, we just plug them in and then multiply, solve it out. 1 minus 0.4035 squared. And then this one, a careful thing to notice, this is still, it's not in regular inches. Of course, there's the increments of it. So we have to multiply that by to the -6 to cancel out, or to have it to the normal value. So we have the plus and then 4035, the negative 191.667 times 10 to the -6. We have this, we wrote it out. All we got to do is plug it into calculator. So this sigma x equals, and just give me some time to plug it in. 2800 divided by 1 minus, and then we have 0.035 to the square, then multiply that out. 475 times 10 to the -6 plus, and then have the Poisson's ratio, 0.4035. Multiply that by our strain in the y, negative 191.667 times 10 to the -6. Perfect. And for that, we get an answer for our sigma x as 13.3 KSI. So now we're going to do the exact same thing, but now moving on over to sigma y, or for the sigma y instead of, yeah. So now for sigma y, it's very similar equation. These two values just kind of switch in this case. So writing it down, we still have E over 1 minus V squared, which is then, this is how it switches. We have the strain in y plus Poisson's ratio strain in x. So that's the difference between the solving for it. So we're just going to solve it out. We have all the variables. 1 minus 0.4035 squared. Keep it going. 475 times 10 to the -6 plus 0.4033. -191.667 times 10 to the -6. Perfect. So all we got to do is plug it into a calculator. So do that real quick. 28,000 divided by 1 minus 0.4035. We square that. Multiply that all by then 475 times 10 to the -6 plus then our Poisson's ratio over here, 0.4035, and multiply that finally by our strain in x, -191.667 times 10 to the -6. Plug that in, and we get -1.5 times 10 to the -4 KSI, so very small number. All right, and then finally our last equation to find tau, we have tau and the xy is equal to our g, and then of course our gamma xy. So we have it from above, 10,800, multiply that by our value, make sure to multiply times 10 to the -6, 519.630 times 10 to the -6, and we get, let's plug that into a calculator, 10,800, multiply that by -519.630 times 10 to the -6. And that gives us -5.612 KSI also. All right, so a little bit reviewing. Right now, we just use our generalized Hooke's law. We found the state of stress, and now we must move on to Moore's circle. So let me just grab another piece of paper. So we're going to write down our units over here. So what we solved from beforehand, we found out that our sigma x is equal to 13.3 KSI. And then in addition, our sigma y is equal to -1.5 times 10 to the -4 KSI. And then our tau xy is equal to -5.612 KSI. So we now have these values. We have to move on to using Moore's circle to finally get our final answer, our principal stress. So for this, we have to look back. Generally, Moore's circle is just a way to visually represent doing our state of stress transformations for finding it. So normally in this case, before, if you did not use Moore's circle, you'd be using this equation above. We can find our two sigma values, the max and the minimum, from having our x plus our y divided by 2, plus or minus then the square root of this. Practically what we're doing the same thing as this by using Moore's circle, but doing through a graphical representation. So in this case, we know that the equation of a circle is this right here. And then what we do is we just incorporate these two elements into this equation, so we get this. Although it looks very complicated, it's just the way to show how Moore's circle can be used. And now Moore's circle is a step that we're gonna go step by step working on how to use it. And then at the end, when we solve it, I'm going to show how it relates back to this equation over here, but it's a visual representation of that. I'm going to put that away. All right. So moving on, more circle. The first thing that we must do is draw a little grid. Sorry, not the straightest line. It's not the best artist. So how it works first, we have to create 2 points. Our very first point is going to be sigma x, comma, negative tau xy. That's for our first point. So in this case, our very first point would be 13.3, and then negative of negative actually makes it a positive, and it would be 5.6. So let's put 13.3 here. Of course, this is in KSI sigma. This is in tau KSI. All right, so we have 13.3, negative makes a positive. Estimate it's about 5.612, about right here. Now for our next point, we have to have our sigma y, and it's just a regular tau xy. So obviously if you look at this, for this case we have negative 1.5. What we're going to do in this case, since this is such a small number, we're just going to say that sigma y is practically 0 in this case, but only for a graphical representation. Graphical representation. So we're going to still use this as the value, but trying to graph 0.0014 onto this piece of paper is going to be extremely hard, so we're just going to have it as 0 visually. So 0, and then negative 5.612. We now have our second point. Now that we have our 2 points, we have to connect a line across them. Don't have a ruler on hand, so I'll use a little Sharpie XO marker. Boom. Now that we've created a sort of line across, we have to make a little circle. To the best of your ability, make a little, pen broke, make a little circle. Now that we have a little circle, we want to mark the center, and we want to find the center point first. So if we look at it, we know for these center points, what we can do, we know that it's in between this point and this point, so we can add our 2 endpoints, our x and our y together, and divide it by 2, midpoint formula. So it is centered at, just plug that in, 13.3 minus, or plus, and since the minus turns into a minus, 5 points, my bad, not 5.621, we have to use the y value, minus 1.5 times 10 to the negative 4, and for that we get a value of 6.65. So that is where it's centered at, KSI. So we're centered at this value. What we have to do now is we have to find R, because what we're trying to find for how it's graphically represented, our final things, our principal strains, sigma 1 and sigma 2, are these very endpoints. So this right here is sigma 1, and then this right here is sigma 2. These are the 2 values that we're trying to solve for. So if you look at here, what sigma 1 is, it's our center point plus R. Sigma 2 is our center point minus our R. So now we have to find R. The easiest way is just imagine a Pythagorean theorem. We have our x, we have our y, we know what these values are, where we can solve for them, and we can get an R. So use Pythagorean's theorem, a squared plus b squared equals c squared, or in this case, it would be r squared. I'm solving for r. So for our horizontal components, we can have our 13.3 minus our centered to get it. So 13.3 minus 6.65, square that. And then of course our height is just, well, our tau, 5.612. 612, square that. So just put that in calculator, square roots, 13.3 minus 6.5, square that, plus square root, another squared, 5.612, square that, and that gives us an answer of 8.7 KSI for our radius. So our radius right here is equal to 8.7 KSI. Now, as I explained before, this is our sigma 1, this is our sigma 2. It's just our center point plus R and minus R. So let's do that. Sigma 1 is equal to 6.65 plus 13.3. Sigma 2 is equal to 6.65 minus 13.3, which equals, put that in calculator, 6.65 plus 13.3. That equals 15.35 KSI. Do that for 1. 6.65 minus 13.3. And that gives us negative 2.05 KSI. So now the last thing that we have to look for is the tau max. Simply put, the tau max is just the height, the outermost height. And obviously, if we just look at this representation, tau max is just equal to R, which is then, well, R is our 8.7 KSI. So let's just, those are the final answers. Let's rewrite it neatly. Sigma 1 is equal to 15.35 KSI. Sigma 2 is equal to negative 2.05 KSI. And then tau max is equal to 8.7 KSI. That is our final answer. And as I explained before, I'm going to show how it visually does the same thing as before. Let's find the piece of paper. So as I explained before, our principal strain equation is sigma x plus sigma y divided by 2. Well, if we look at this, sigma x plus sigma y divided by 2, that's what we did to find a centered at. We did our x right here minus our y, and we divided by 2. So if we look at the original equation, this is what our midpoint is. Then we do plus or minus the square root of sigma x minus sigma y over 2 squared plus then tau xy. If we look here, that's what we solved for R. 13.3 minus 6.3, same thing, x minus y. Obviously, it wasn't divided by 2, but that's because we did previously. But same principle applies. We're squared, and then we have our tau squared. Final answer, we now get our R. We do our plus or minus, as we explained here. Plus or minus here, and then boom. So really, the math that we just did here, we did exactly the same thing here, just broken up into multiple steps. And this is a visual way to represent how to find the principal stresses. So a little final recap what we did for our problems. We started off with our strain gauge data from the very beginning, what was given to us. We then moved on, used our strain rosettes to find the state of strain. Strain rosettes right here. We used them, we got 2 equations, 2 unknowns. I used a matrix in this case. You can do any other way that you like to solve it. And then we had our values. The x, the y, and then the gamma. Then moving on, our next step, we decided to go left on here, was generalized Hooke's law. For this, the generalized Hooke's law, to give us then our x, y, and z, or x, sigma, y, and then the tau xy. And before that, we had to solve for these constants, our e, g, and Poissons. This was in our textbook. This we had to solve using this equation. So now that we got those problems, we now finally moved on. We got our state of stresses. We then finally used Moore's circle in this case, used Moore's circle, did it all the way throughout, and found our principal stress. So overall, that's the way to solve this problem. Breaking it down. Hopefully that was a good enough explanation, and hope you have a nice day, Professor. How do I end this recording?